Today we're going to talk about the fundamental theorem of calculus. As its name implies, this is a really key thing in calculus. It ties differential calculus and integral calculus together and makes it all one. Now, we've already used the fundamental theorem somewhat. On pages 273 and 274 in your book, it talks about that if you have a definite integral that looks like this, that what you do is you find the antiderivative and evaluate it at the top limit, and then use the antiderivative and evaluate it at the lower limit. And this is the area under the curve, remember, from A to B under this curve. So it's an accumulation function. It's how much of the change accumulates over time. Okay, this is actually part 2 of the fundamental theorem of calculus. But there's something else that we need. We need the part 1 that goes with it. So I'm going to give it to you, and then we'll kind of talk through it, and hopefully it'll make sense. So for part 1, so this is part 2, which we've already dealt with. If this is part 1 of the fundamental theorem says, if f is continuous on a closed interval from A to B, then the function capital F of x equals the integral, the definite integral from A to x of f at t dt. This function has a derivative at every point x in this closed interval from A to B, and the derivative of this capital F function, so the derivative of this stuff right here, the integral from A to x, f at t dt, equals lowercase f at x. Now, we've looked at this a little bit with the calculator and the projects that we've been doing on the calculator, so hopefully that gives you a little bit of background to be able to deal with this. But basically what this is saying is, just like adding and subtracting are opposites of each other, taking the derivative and taking the integral are opposites of each other. So the derivative of the antiderivative is just the original function. That's all it's saying. So when you see this notation here, then you don't actually have to integrate it and then take the derivative. You just can go straight to here. Now, let's look at how this works. So for example, if we want to take the derivative of this function, remember it's a function because it's a definite integral with a variable bound. Okay, when we had the definite integral where they're both numbers, we ended up with just a number because it gave us the area under the curve, a straight number. This is giving us a function where we can plug in different x values to find out the area at different bounds. So if we're taking the derivative of this, we have 1 over, well, it doesn't matter what your lower bound was. Remember, we looked at this on the calculator and how the lower bound, all it changed was by a constant. The slope of that line is still the same, so its derivative is still the same. So we take the derivative, and we've just got a number here and then our x here, so that means it's just 1 over 1 plus x cubed. We don't actually have to integrate this and then take the derivative. Because of the fundamental theorem of calculus, we know that this is true. So sometimes you have to use the chain rule. What happens if we want to do the derivative from 1 to 1 plus 3x over 1 over t dt? So this function here, it's not, this is f of x. This is the antiderivative function at x. This is our antiderivative function at 1 plus 3x, because that's what our variable equation is for this. So we have just the constant on the bottom, that's what we want, and then whatever you have on this top bound here, then that's what your input is for your function. So if you want to take the derivative, this is the derivative of this antiderivative function, okay? But we have to use the chain rule, so we have to take the derivative of the inside too. Okay, we've got the derivative of the outside part, which is the antiderivative function. So we take the derivative of the antiderivative function. Wow, that's a mouthful. And then you have to take the derivative of the inside. So we took the derivative of the outside and then take the derivative of the inside. So what's the derivative here? Well, this is just this function evaluated at this input. So we've got 1 over 1 plus 3x times, and then we take the derivative of that input, 3. So we just end up with 3 over 1 plus 3x. Here it's a similar thing, except the derivative of the inside part is just 1, so we don't really need to put anything for that. But it's the chain rule. That's all it is. Take the derivative of the outside, then take the derivative of the inside. Okay, now, the hard part comes in when, oh well, here, let's do one more of these just to make sure. I want you to pause the video after I write this problem out and do this one on your own to make sure that you've got this, and then we'll deal with what the hard part is. So pause it now and see if you can get this on your own. Alright, so we take the derivative of this is the antiderivative function at x squared. So we take the derivative of the antiderivative evaluated at that part times the derivative of what's inside of what we're inputting. So we end up with 2 over x. So this is our answer. Hopefully that's what you got. If you're having trouble with this still, then make sure you ask about it. Now, what happens if we confuse the issue a little bit, and instead of having our variable on the top, we have it on the bottom? Well, actually that's a pretty easy fix. So we know that the integral from x to 1 of t dt is equal to negative the integral from 1 to x of t dt. That's one of our rules we talked about definite integrals. So what we need to do is use this so that we can get our variable as the upper bound. Because for the fundamental theorem of calculus to work, you have to have a constant on the lower bound and a variable equation of some kind on the upper bound. So that means this is equal to the derivative with respect to x of negative the integral from 1 to x of t dt, which we know from our derivative rules that we can just pull this negative out here. Don't you love how this all works together? Makes so much sense. So the derivative of this is x, because we just take this function evaluated here. You don't have to use a chain rule because it's just x. And then we've got our negative sign out front. So the derivative is negative x. So if you have a variable in the bottom, you have to get it up to the top. Now sometimes you're going to have something more complicated. What if I want to take the derivative with respect to x of the integral from x to x squared of e to the t dt? Now, we can't have a variable down here, but we know that we can split an integral up into pieces. So let's look at how that will help us. If we're going from x to x squared, we can change that to the integral from x to 0 plus the integral from 0 to x squared. Now you say, we don't know that 0 is between x and x squared. Well, that's true, we don't. But it'll take care of itself with the signs of the different, if, for example, let's see, e to the x. So if x is here and x is squared is here, then this one here would be this area, and this one here would be this whole area here. But if we're going from x to 0, this would be a negative area. So what would happen to this negative area? That's right, we would subtract it off, and we would still end up with this, because this would be a negative area, and it would go away. So we'd still end up with the x to x squared. Now, let's see. We have a variable in the bottom now, so we don't want that. So we'd use our integral rules and switch that. So now we have a little bit easier function to deal with, because we've got a constant in the bottom and our upper bounds are variable functions. Now, does the constant have to be 0? Absolutely not. You can make it whatever you want, as long as it's the same for both of them, because then you're taking the integral. You're not skipping any pieces of the graph to take the integral. So this can be rewritten as the derivative, and I'm going to rewrite it so it's this one minus this, just to make the negatives look easier to deal with. From 0 to x squared of e to the t dt minus the integral from 0 to x of e to t dt. And of course, with our derivative rules, clear some space in here. With our derivative rules, we know we can split that up. Actually, that goes all the way back to limit rules, which gave us the derivative rules, which give us integral rules and everything else. So they're all related to each other, but we know we can split that up. So we'll take the derivative of the first part minus the derivative of the second part. So we've got this function here we're taking the derivative of. So that means that it's that inside part evaluated at this upper bound times the derivative of the upper bound, that chain rule. And then here we've got the derivative of this function is this inside part evaluated at the upper bound, and then chain rule just gives us times 1, so it's not something we need to worry about. So we have, this is our answer if we just neaten it up a little bit. So for fundamental theorem of calculus, you've got to have a constant in the bottom and then some kind of variable function at the top. Don't forget to use the chain rule if it's not x. Basically, all this is dealing with is taking the derivative of integral functions. So remember, these here, these are functions. If you try to graph this, you're going to get a picture. You're going to get a graph. Because what this is telling you is the area under this curve, e to the t, from 0 to x squared, whatever x squared happens to be. So at x equals 1, you'll have one value. At x equals 2, you'll have one value, and so on and so forth. And so that gives you a function that you can graph. Make sure you have read this section thoroughly. There's some proofs in there for this theorem that you need to understand and you need to be able to identify. Make sure you're really comfortable with this kind of notation. They will put this on the AP exam. More often than not, they put it on the AP exam, and then people will try to take the integral and then try to take the derivative from that, and it gets all long and complicated, whereas if you just remember the fundamental theorem of calculus, it's pretty basic and easy. So make sure that you have read through this section, looked over all the examples, watch the Khan video. Khan has a whole section of videos on fundamental theorem of calculus if you would like. Make sure that you understand this. This is fundamental for your understanding of calculus, so make sure you've got it down. If you have questions, write those down so that we can answer those in class.